for a lead on this project. I have an interest in both the software and hardware, and I help specifically build and program the application and Bluetooth low energy components.
The figure shown in the next slide illustrates the big picture of our project. As you can see, the person running and the car driving are both putting stress onto a piezoelectric transducer material, which generates electrical power in order to light up the street lights. This is a clean and efficient way for anyone to help generate some kind of power. We want people to be able to easily have access to the benefits of electricity while keeping them informed along the way. The way our power infrastructure is set up, people are always looking for new ways to generate electrical power. Our grid nowadays relies heavily on fossil fuels, which obviously is bad for the environment. It is revolutionary to put the means of clean power generation in the hands of the consumers themselves.
So the problem to be addressed is can be defined as the need for better methods of harnessing energy in a manner that is both possible and beneficial to the average consumer. By turning the user's kinetic activity into easily consumable electrical power, we seek to help users increase their energy levels, both physically and electrically. We also seek to provide them with a way to easily access the data regarding their system's individual usage, such as how much power they've been generating and how much they currently have stored. Because of the nature of our project, we go so far as to label it green, since it accomplishes a reduction of a user's carbon footprint. There's a strong need for cleaner energy sources for society, because pollution has become a major concern, it's contributing to the global warming crisis that the Earth is actually facing right now. And so according to the U.S. Energy Information Administration, fossil fuels account for the majority of electricity generated in the United States in 2018. So clearly, generating energy by such means would not require any harmful materials that would pose a risk to the environment.
So here we have a physical diagram of our system. It is a level 0 description with 4 individual level 1 subsystems. The 0 subsystem takes in kinetic energy and outputs usable electrical power as well as data. 4 subsystems consist of the generation subsystem, which harnesses the power from the piezoelectrics and store that power in the storage to later be sent out in the transmission subsystem. And we data management subsystem in order to monitor all of this while it goes on.
These are just some equations used for the hardware aspect of our project. They relate to the power and energy dynamics of our system. As you can see in figure 7, you can see the waveforms of the EH301A module, which is an energy harvesting module.
For the software, we developed a custom application was written in Java so that it could provide an environment for implementing Bluetooth low energy communication that enables communication between the application and the BLE chip. BLE utilizes a gap profile, which is a general method for sending and receiving short pieces of data known as attributes over a wireless link. These attributes work by first employing a GATT server that is advertised by the BLE chip. The server consists of a GATT service, which consists of characteristics. And characteristics are the actual data values. So the services essentially act as an organizer for data values, followed by descriptors, which provide information about those data values.
This image in the slide shows all of our hardware components used for this project. In the top portion of the image, you can see our full wave rectified piezoelectric transducers and the EH301 energy harvesting module that I mentioned beforehand, which comprises our generation subsystem. In the bottom left corner, you can see our storage subsystem, comprising of 8 rechargeable AA batteries in their respective cells, each with capacities of 2,800 milliampere hours. In the bottom right corner, you can see the key transmitter used for a transmission subsystem. Single pole, double throw SPDT switches, along with our 1N 4001 GT diodes that we use for full wave rectification, were employed to ensure a proper flow of current. We will go into more detail for the individual subsystems in the following slides. Next. From the image here, you can see that the subsystem, it consists of parallel configured piezoelectric transducer devices, which are full wave rectified, which that means it converts the original AC power that was generated and it switches it to DC power in order to avoid destructive wave interference along the supply line. These lines are fed into the EH301A energy harvesting module. This module acts like essentially a smart capacitor. It allows accumulated charge to be burst into storage. Theoretically, this module's useful energy output is 55 millijoules of energy per cycle from various types of electrical sources, which can be used to power conventional 3.3 volt and 5 volt devices. But that's assuming the module doesn't have any energy input during firing mode. With only 4 of these small piezos, we were able to trigger the EH301 within a couple of minutes. With more of them, the power output of the generation system could easily supply 17.2 watts of power. In the image here, you can see there's 8 AA nickel metal hydride rechargeable batteries displayed with their respective cells. They are charged up from the EH301A energy harvesting module and are discharged when they need to supply power to the key transmitter, which will supply to charge any mobile device that utilizes a key receiver. In our case, the user's mobile device. The Pololu 5 volt step up, step down voltage regulator is utilized to ensure a steady 5 volt output. The function of this subsystem is simulated with Simulink. The battery elements were modeled to reflect the characteristics of our EBL AA batteries. Shown here is the simulation of our system charging from 5%. The input models, the EH301 operating at a duty cycle of 1, assuming a constant power input. The simulation was run for 11.11 hours, or approximately 70,000 joule inputs. The relevant outputs shown include the subsystem's input current, as well as the input current of an arbitrary battery. Also, the battery's voltage and its state of charge. Shown here is a simulation of our system discharging down from 98%. The output models a current draw of 1.5 amp, which represents the average value of the key transmitter. This simulation was run for 3.94 hours, or approximately 70,000 joules output. Here we see the voltage of an arbitrary series branch of batteries. As before, a battery's input current, its voltage levels, and its state of charge are shown. Since the flow of power must go from our kinetic input to our electrical output, switching circuitry was deemed necessary for our purposes. The schematic shown illustrates how we were able to switch the AA batteries from being in a parallel configuration when they are charging to a double series branch configuration when they are discharging, supplying power to the transmission. This setup optimizes the flow of both inward and outward power. In the image here, you can see there is a universal key standard wireless charging transmitter and receiver. The transmitter will use the power stored into the rechargeable AA batteries in order to supply charge to the receiver. Once the user places the mobile device on the coiled platform, a charge will be applied and the mobile device will acknowledge that it is indeed charging its battery. Through our experimentation, we determined that the transmitter has a power factor of approximately 50%, and theoretically, we were able to show that this value is reasonable because of the power loss inherent in the MOSFET transistor switching at a resonator circuit.
So with our software design, we wanted to implement a way that our hardware subsystems could provide users with a valuable interface that shows them the charge levels So to set up BLE on the application, we first need to set up BLE permissions before the mobile device's BLE adapter can be initialized. The application does this by first scanning for BLE devices and then connect to our BLE device through its GAT server. Once a successful connection is established, the BLE attributes such as the services and characteristics are then read from the connected BLE device. And then our application is then set up to receive updates of the data as they come. So for the data, for our application to transfer data from the hardware, we needed to program our application to communicate with the Cypress BLE chip. We set up the BLE chip by implementing the GAT profile along with its characteristics such as the voltage of the hardware subsystems. Next, we needed to set up parameters such as the advertising and scanning time so that the application would be able to discover the BLE chip. And once the BLE chip is paired, then data transfer can be initiated. Currently, we are successfully transmitting and displaying data in the logs of our custom application. As highlighted in the screenshot there of the application logs, you can see that the application is scanning for nearby BLE devices, where it builds a record of each device's MAC address. After scanning, the application confirms that it has connected to our BLE chip, which you can see has a MAC address of 008050000002. And after it discovers the BLE chip services and characteristics, and with these logs, we are able to obtain the UUIDs for our BLE chip, which is what provides the data.
So here we have unit test 1, and the purpose of this test was so that we could test each of the piezoelectric transducers as they were made, to ensure that all the soldering was done correctly on them as they had to be full wave rectified. Here is unit test 2, where we tested the full wave rectifiers before they were attached. That was a first step of the soldering process. With the EH301A module being the most expensive part of our project, we had to test it and ensure that it worked how we needed it to. That's what the purpose of this test was designed to do. For unit test 4, this was also a test on the wireless transmission subsystem, as in order to achieve that aspect of the project, we used the key standard. Integration test 1 was of the generation subsystem. Completion of this test showed we were able to generate the power from Piezoelectrics and then put it into a usable, storable form using EH301. Integration test 2 was of our storage subsystem. We succeeded in simulating this, as was shown by our test results, and we concluded that the way it was designed and how we were going to put it together, it would have successfully met its standards. And for integration test 3, we tested the data subsystem, and also here, some aspects had to be simulated. On that later, but we considered the test a success. All of our subsystems successfully tested. We considered our acceptance test successfully simulated. So, yay. And for our corrective actions and durations table here, you can see a quick graph of our progress that we made during the time.
So the coronavirus has provided us with some unprecedented, unique challenges for our Capstone project. Some that might have been proven too difficult to overcome initially. And so once we realized the potential severity of the COVID-19 outbreak and the impact that it might have caused for the rest of the academic year, we instilled a contingency plan. So as you can see on the table in the slide, there were a couple of things that we had to rethink in order to get the final objective. So the biggest issue we faced was due to the coronavirus pandemic was the lack of lab equipment. So as it stands, our project is complete, but there are some improvements we would like to implement in the future. With lab equipment, we could work on implementing the simulated hardware designs, and with respect to the software, we'd like to work on presenting data in a nicer format within the application menu instead of the logs. So given more time, we'd like to further optimize the system by increasing its efficiency and data tracking capabilities. Overall, we think it was a really great hands-on experience.
So here we have a cost analysis and bill of material. I won't spend too much time on it, but the sum total we spent was almost $257, which is only $7 over our allotted budget. And here we have a project demonstration video.
As you can see in the video, we are showcasing the generation capabilities of the piezoelectric transducer devices in order to prove that the generating power is necessary. As you can see, the spikes shown on the oscilloscope depict electrical power being generated every time we apply a stress onto the transducer material. There's voltage spikes of approximately 20 to 40 volts for each spike that we hit in this video. Software.
So for the software demonstration, we could see that the blinking green LED on the left side of the BLE chip indicates that it was advertising. And once I open the app, we could see that a connection is made to the BLE chip where it scans the BLE chip for characteristics. And the data of interest is for the highlighted MAC address. That tells us the BLE chip is successfully paired and that we now have access to all the services within the BLE chip.
So as you can see here, we were adhering to 7.8 IEEE Code of Ethics. Number one being safety. We determined that it was a very important consideration for our design process. Each group member ensured that all designs and parts used maintained the highest safety standards and protocols as to pose no dangers to the public or the environment. As you can see, number three is the openness. So what that means is we disclosed all of our findings. We didn't hide anything from the public or anything. We weren't misleading with any of the specifications listed. Five is wirelessly transmitting. This clean power allows for easy access. It was very important for us to provide easy access. Making the supply of green energy more accessible decreases the generation consumption of unclean, non-renewable resources. This project demonstrates that the more green energy technologies get researched, the more efficient and implemented they become. As you can see, number 7, take feedback and criticism. So we were always taking constructive feedback and criticism and improving upon a project. The professors and the faculty have been very, very helpful with this project, and I express great gratitude to them for that. 8 is no discrimination. So as it sounds like with our project, we did not discriminate against any race, sex, or creed. We hope to be able to share the fruits of this labor with everyone.
So for this project, we took into account a lot of ethical issues so that we didn't make any uninformed decisions that would have repercussions. In the beginning stage of the project, we were researching designs for a possible apparatus that would not discriminate against any one kind of person. The apparatus that we decided on, which made the most sense in terms of being ethical and efficient, was a pair of shoes. people who do and do not have physical impairments would be able to wear shoes for its functionality and for its foot protection. For the BLE portion of our mobile application, we had to base it on Advanced Encryption Standard 128, which just ensures that the data being transmitted is secure. It effectively minimizes the risk of any possible data compromise. So we would be held liable if the user's data was stolen. So we took that very seriously.
And this is just a quick slide on the references used throughout the presentation. I'd like to thank the school for watching, and are there any questions?
I just two comments. It was a nicely done presentation. I particularly like the part about the your thoroughness, your diligence with the modular testing. One thing that I think would have been nice up front would have been some reference to current work or prior work that would have been in this area, maybe relevant or that you would have been motivated by it. So it was a nice, clean presentation.
Thank you.
Thank you. We'll definitely take that into consideration.
I have another question. First of all, compliments, very nice work, high quality of work. Did you do any noise measurements? Because I see a lot of capacitance components, and this can produce some kind of noise on your system.
I'm not sure exactly what you mean, but when we were first experimenting with that EH301 smart capacitor, it actually can self-charge up to 1 millijoule from just Gaussian noise.
Was causing or not causing?
Perhaps I'm misusing the term. Just the noise when you're measuring stuff in the lab.
Did you measure this noise? What effect can it have on the fall time of your system?
On the what?
You saw some diagrams there and some experimental arrangements with using the oscilloscope. Did you measure the noise of your system?
Not directly, no. I mean, when you hook up the...
Thank you for the suggestion. No, we'll definitely, when we're moving forward with this project, we'll definitely consider the noise levels.
How did you consider the noise level based on which approach?
I'm not entirely sure how noise project. Any noise would just serve to better generate power into the system anyways, if it could be hard.
Battery, no, let me tell you, battery does not generate noise. Battery is good approach. If you could have a power line, yes, you could have 120 volt hertz noise, but not in battery. I'm talking about noise introduced due to you have large capacitance in your system. That's my concern. From battery point of view, you are set up very smart way, but you have a lot of capacitors.
If the switches, we only have the one capacitor, the EH301, and that consists of 2 big capacitors and some intel.
Even the electrodes are firm capacitors. Everything is a capacitive system.
Yes. Well, that's if we would have to insulate the system, yes.
This is the way, and the insulation at this point at low frequency is very difficult. You have to get special insulation procedures. You have to put foils around, aluminum foils. There are special procedures to follow. Anyway, the quality of your presentation was very good. If you like, you can add about few words about noise, in the description or the discussion of your system, what measures could you take, etc., just to enhance the engineering component. Otherwise, excellent work. Thank you very much.
Thank you.
Thank you.
Any other questions?
Thank you, Alberto, and thank you, Andrew and Nicholas.
Thank you.
Good job. I would advise you to take Dr. Yakov's suggestion seriously. And
Yes, absolutely.
I'll introduce the next team if they are here. So I would like to introduce Aina, Makji, and Tim, who's presenting facial recognition for restaurants. Guys, who's going to share the screen?
I think Tim is.
Yeah, I think Tim's working on it.
Okay. Tim, are you here?
He
Yeah,
said
his
he needs a
screen is
second.
frozen.
Okay.